Okay, so chapter 4 is an introduction to chemical reactions. I have to say that this chapter has quite a lot of material. It's kind of a survey of everything that we need to know about reactions, and unfortunately, you just kind of have to go with it at first. Some of the things we won't even learn more about until the second semester. We'll kind of go into more detail. But anyway, just bear with me, and this is a general introduction to chemical reactions. Okay, so first of all, when you talk about a solution is a homogeneous mixture of two or more substances. So just a few definitions. The solute is the thing that is being dissolved, and the solvent is what it is being dissolved in. So of course, if you're, for example, if you make a saltwater solution, your salt would be your solute and the water would be the solvent. Water is a very important solvent. And so in general, if you see the word aqueous, you can just assume that water is the solvent. So it may not specifically say water is the solvent, but if you see the words aqueous, that's what it means. And lots of substances can dissolve in water. But then we also want to look at the way that things dissolve in water. So we can classify substances that either give ions when they dissolve in water or molecules when they dissolve in water. Okay, so the ionic theory of solutions, and I think there's a lot of misunderstandings about what's happening when things dissolve in water, regardless of if there are ions or not. But let's specifically look at ions. Okay, so what happens when you have an ionic compound that dissolves? It actually breaks apart into the different ions that are then free to move around. Okay, so for example, if you put some salt into water, NaCl, it will break up into the Na plus ions and the Cl negative ions. And the way that it does that, we'll see on the next slide, they dissociate because they are now independent of each other. And they are electrolytes because they are charged particles. And so actually, because you have charged particles hanging around in water, they're capable of conducting electricity, and so that's why they're called electrolytes. So actually, it's very interesting because pure water, if you just had pure water without anything dissolved in it, which is actually very hard to do, it would not be a very good conductor of electricity. It's actually all the dissolved things, all the dissolved solutes that are in the water that create this, make it electrical. Okay. Let's see, so not all electrolytes are ionic compounds. Some molecular compounds also dissociate into ions. This is it's kind of in the middle. So the thing in chemistry is it's not black or white. There's a lot in the gray in the middle. So hydrochloric acid, HCl, is actually can break apart also into its ions H plus and Cl negative, as you can see in this slide. It's also electrical conducting. So it's also these are also electrolytes. Okay, and then some molecular compounds also dissolve but do not dissociate into ions, and these would be things like sugar, glucose. When you put glucose in water, all that happens is that the different molecules move apart from each other. And I think in a minute I have some pictures here that can help you. So if these kind of compounds that just get dissolved in water but don't form ionic compounds, they would be considered non-electrolytes, and they do not conduct electricity. You see a link here at this PFET. I would, if you can pull up the PowerPoints later for yourself, and you want a link on this, and I have a link for it also on Blackboard. It's a really fun simulation where you can look around, and it shows you different sugar and salt solutions and how they act when they're dissolved in water. And I have a separate little very short video that you can watch where it's sort of describing salt solutions being dissolved in water that I kind of walk through a little bit of the simulation. So anyway, check that out. Okay, so It's not, again, like I said, not black or white. It's not that they all dissolve or they don't dissolve. Actually, some ionic compounds don't dissolve as well, and you're probably familiar with this as well because you know, if you try to put chalk in water, it doesn't dissolve very well. If you put salt in, it does dissolve well, but at some point it sort of stops. So if something does dissolve well and breaks apart totally, we call it a strong electrolyte. And so sodium chloride is an example of that. Most ionic solvents are strong electrolytes. However, there are some that don't dissolve well. And in fact, what they do is form a precipitate. So you may be familiar with that. And you'll experience that in lab a little bit. And I'll show you an example in a little while. And then if something doesn't dissolve very well, it's called a weak electrolyte. So it dissolves a little bit. There's a small percentage of ions that dissolve. An example of that is ammonium hydroxide. You can see the double arrows kind of represent the fact that it doesn't completely go to the right or the left. So some are broken apart, some are not broken apart. And so it's a weak electrolyte. Most soluble molecular compounds, as you can see, are either non-electrolytes or electrolytes. Okay, so what's actually happening in the water? And it's a little bit hard for me to show you this, so I would highly recommend either clicking on this link to watch this YouTube video right over here, which shows you the dissociation of ions in solution. I think it's a very visual thing. Or also make sure and check out some of the other videos that I have links to. Tyler DeWitt does a really good job talking about what happens when things dissolve. But what really happens is that the water, we know that water is a polar molecule, which actually we will talk more about later in the semester, but water has a negative end and a positive end. The negative ends are attracted to the positive ions, the positive sodium ions. And so what happens is they will go into the salt crystal and pull out the sodium ions, surround them and pull them out. And then the positive ends of water will go in and surround a chloride ion, the negative ion, and pull it out. And so what you have is a bunch of sodium ions surrounded by the negative ions of the negative ends of water, and then the chloride ions surrounded by the positive ends. And now they're free to move around in their container as much as they want to. And so that is what happens. Again, I would highly recommend watching that little video. I can't show it to you here because I'm just doing my PowerPoint. All right, so how can you decide by just looking at a compound if something is soluble or not soluble? Well, you can look them up, but we also have solubility rules, which if you just kind of take the rules and go through what we're going to do in just a second, we can predict if something will dissolve in water or not dissolve in water. And this is mainly here we're talking about ionic compounds. Okay, so just some more definitions. If something dissolves readily, we call it soluble. It's able to dissolve. And if something doesn't dissolve, it's insoluble. Okay, so here are some of our solubility rules. And again, we learn more about this as the semester goes on and as the year goes on. So at this point, you're just kind of going to have to learn the rules and learn how to apply the rules. Okay, so the solubility rules, again, this would be a really good thing to either copy or write down or get in your head somehow. All of the group 1A ions, lithium, sodium, potassium, rubidium, and ammonium, NH4+, one of the polyatomic ions, those, no matter what they're paired up with, that compound will be soluble. So if one of those ions is in a compound, it will be soluble no matter what. The same thing is true for any acetates, C2H3O2 negative ions, and anything containing the nitrate ions, NO3 negative. So you can see there are no exceptions. All right, if you look at rule number 3, if you've got a compound that has chlorine, chloride, bromide, or iodide, most of the time they're soluble. And especially, rule 1 and 2, or rule 1 would supersede anything else. So if they're paired up with lithium, sodium, potassium, rubidium, ammonium, then they're definitely soluble. Most other chlorides, bromides, and iodides are soluble, but you can see over at the right there are a few exceptions. So chloride ions will not dissolve if they're paired up with silver, mercury, or lead. Same thing with bromine, same thing with iodine. So most of them are soluble except for those exceptions. Okay, the same thing is true for sulfates. Most sulfates are soluble, but again, you can see that there's a few exceptions that are not soluble. Now, as we keep going down, we're going to sort of flip, and so we'll see that, for example, carbonates, most carbonate compounds are not soluble. The only exceptions to that rule are group 1A, lithium, sodium, potassium, rubidium, and ammonium. So rule number 1 sort of applies here. And then the same thing for rule 6. Most phosphates are not soluble unless they're paired up with the group 1A or ammonium ions. Most sulfides are insoluble, and most hydroxides are insoluble unless they're paired up with the 1A ions or ammonium. And then actually you can see the hydroxides, a few more hydroxides are also soluble: calcium, strontium, and barium. Again, you might want to check out this PFET link. It's a simulation that you can kind of play around with, and you can see different soluble salts. All right, so let's using those rules figure out if the following compounds are soluble or insoluble. So sodium carbonate. Well, right away, our first rule says that anything that has sodium in it will be soluble. So sodium carbonate, even though most carbonates are not soluble, all sodium ions are soluble, and so this compound should be soluble. Okay, lead sulfate. Most sulfates are not soluble, and lead is not an exception, and so this will be insoluble. Okay, cobalt hydroxide. Again, if we don't have any rules for cobalt, but we do have a rule for hydroxide. It says most hydroxides are insoluble, and cobalt is not an exception. So again, cobalt hydroxide would not be soluble. Okay, barium nitrate. Well, again, we don't have any rules for barium, but we do have rule number 2 that says all nitrates are soluble. So this compound should be soluble because it contains nitrates. And then the last one, you probably can see that all compounds that have ammonium ions, NH4,3, are also soluble. So that's how you use the solubility rules. All right, now how can we represent different compounds in equations? We're going to learn how to write molecular and ionic equations. All right, so a molecular equation, as you would imagine, is one that has molecules written into it. However, they might actually exist in solution, so we're actually representing them in an equation as a molecule. However, they're probably more likely to be ions in solution, or at least some of them. So we have different ways to write this. So this is an example of a molecular equation. Calcium hydroxide plus sodium carbonate yields calcium carbonate and sodium hydroxide. Okay, but what you especially want to notice is that the calcium hydroxide we already know is a soluble if you look up on the solubility rules, and so you see in parentheses AQ listed next to it. Sodium carbonate, again, all things that have sodium in it are soluble, so that's aqueous. The calcium carbonate, however, is a solid. And actually, even if you didn't know your solubility rules, just having those letters listed after the compound will tell you that the first two reactants are aqueous. They're soluble in water. The calcium carbonate is not soluble in water, but the sodium hydroxide is. It's aqueous. Okay, so we can indicate. So a molecular compound has to indicate what the state of what the state is. Is it a solid? Is it dissolved in water? AQ. Now, if we want to write this as a more true form, as an ionic equation, what we're going to do is break apart any strong electrolyte. So anything that has AQ following it needs to be written as separate independent ions, because that's actually the way that they are in solution, and it's a more accurate representation. So if we look at the previous equation, we see that calcium and hydroxide can be broken apart, both aqueous, and just keep in mind when calcium and hydroxide break apart, even though it's Ca parentheses OH2, each of those hydroxides are moving away from the calcium. So there's 3 particles and they all move in their own different directions. So that's why the 2 comes out front of the hydroxide. There are 2 of the hydroxides and they each are independent of the other. So we don't write them as OH2, we write them as 2OH. Okay, and then same thing with sodium carbonate. Sodium, there's 2 sodium, so the 2 comes out front. There's 2 Na plus, and then CO3 negative 2. It's really helpful to learn your polyatomic ions because they will haunt you the rest of the year if you don't really become comfortable with them. All right. Now we see the product. Notice that calcium carbonate, which has a S solid after it, is not represented as independent ions because when it's in solution, it stays together. It is a solid; it won't dissolve. And sometimes sometimes we write a little arrow showing that that's a precipitate that a solid forms and sinks to the bottom. Okay, and then for 2 sodium hydroxide, the 2 distributes, and so we have 2 sodiums and 2 hydroxides. So you can see that anything that was aqueous to start with has now been broken up into ions. Here's another example. Na2SO4 plus CuCl2. Both of those are aqueous, so you can see below that the sodium, 2 sodium plus SO4 negative 2, the sulfate ion, plus copper 2 plus 2 Cl negatives, those are all broken apart. And then the 2 NaCl are broken apart into 2 Na plus 2 Cl negative. But the copper sulfate, which is not soluble, which is in solid form, is still kept together. So this is called a complete ionic equation, the complete ionic equation, because all of our ions are written. And one difference from the last slide is that I haven't put any of the aqueous or solid in parentheses. If you're writing them like this, then you know that if they're separate, they have to be aqueous, and if they're not separate, they have to be solid. But now notice that we have 2 sodiums on the left, 2 sodiums on the right. We also have 2 chlorides on the left and 2 chlorides on the right. So we can actually, they're the same on both sides, so we can actually cancel them out. Okay, so since we can see that the sodium and chloride are identical on both sides, and that means they don't take part in the reaction. They're called spectator ions. A spectator ion is just one that does not take part in the reaction, just like spectators don't take part in the game. At a football game, the spectators don't take a part. So we can actually omit them from the equation, and that leaves us with the net ionic equation. The net ionic equation is the chemical equation where the spectators have been removed, and so it's really the important part of the reaction. So in this case, the copper ion plus the sulfate ion combine to form copper sulfate precipitate. Keep in mind that charges must be preserved, so the sum of all the charges on one side should be the same as the charges on the other side. They may not always be 0, but they have to be equal to each other. So we can see in this case, copper is a 2 plus, sulfate's a negative 2, so it has a total charge of 0, and of course the copper sulfate is solid, is neutral, and so it's also 0. Now, if it turns out that every ion in a complete ionic equation is a spectator, then what that means is there's really no reaction that has occurred. All right, so let's try another example. we start with a molecular equation that is given to us. So if we look at that, 2HNO3 aqueous plus MgOH2 solid gives us 2H2O liquid plus MgNO3 aqueous. So keep in mind that the only things that break apart are the aqueous. So in this case, this is the first time we've seen a liquid. A liquid will stay put together and a solid will stay put together. So the HNO3 will break up into H plus and NO3 negative, and there's two of each of them. Okay, so you can see that. Look at it. All right, so the H plus and the NO3 negative get broken apart, and there's two of each of them. The MgOH2, which is a solid, stays together. The two waters, which are liquids, stay together, and then the Mg and the NO3 breaks apart. So there's two NO3s, one Mg. Mg, remember, is a 2 plus. All right, so now do we have any spectator ions? Yes, we do. The nitrate shows up both on the left and on the right, two of them. And so we out. And this gives us, let's see, here we go. We can cancel them out. And so that gives us the essential reaction, which is also called the net ionic equation. All right, and notice this one, like I said, the charges don't always have to be zero on both sides. If you look at the left-hand side of the arrow, you've got two H pluses, so a +2. The magnesium hydroxide is 0, so overall on the left is a +2. And on the right, we have 0 plus, again, a +2. So they're equal on both sides. Obviously, what's not in here is that the nitrate, the negative charges have been canceled out, but it doesn't mean that they're not there. It just means that they don't take part in the reaction. So just as a summary, what are the steps in writing a net ionic equation? First, take the balanced molecular equation, and you might want to just take a minute and make sure that it's balanced. Rewrite the equation showing the ions when a strong electrolyte dissociates. A couple of things to remember. Remember that when there's a subscript for an ion, that will usually come around front, like say if there's two hydroxides or two chlorides or whatever, that will come out front because those break apart individually from the positive ion. So don't forget to pull those out front. And then also don't forget that if there's a 2 in front of the whole thing or any number in front of the whole thing, you need to distribute that to every ion that is broken apart from the compound. And then identify any spectator ions and cancel them out, and then you'll have your net ionic equation. All right, so let's just look at a couple of different types of chemical reactions that we might encounter. They're going to fall into one of these following categories. Precipitation reactions, which is where a solid forms. Acid-base reactions. Acid-base, you're probably all familiar with acids and bases, but there's basically a transfer of an H plus ion. Or then oxidation-reduction reactions. Okay. So we've already looked, we saw one example of a precipitation reaction, and now let's look at them a little bit more closely. A precipitation reaction is one where aqueous solutions combine to form one insoluble product. So a precipitate is just an insoluble solid compound formed during a chemical reaction. For example, let's look at, I think we've got it written here. Okay, so if you react NaCl, and you can see it's got AQ, so it's Na and the Cl are totally dissolved. The silver and the nitrate are totally dissolved. And if you go back and think of your solubility rules, both anything with sodium and anything with nitrate should be soluble. But then when the silver and the chloride come together, they cannot stay dissolved. Their pull for each other is too strong, and so they will actually form a solid and not stay dissolved in the liquid. But then the sodium and the nitrate will stay dissolved. So silver chloride is the precipitate. So how can we predict if a precipitate will occur or not? Well, again, we're going to use our solubility rules, and we're going to be able to we're going to write our reactions. Now, you may have to. So far, we've looked at equations that have told you if something was aqueous or not, and so now we're just going to use our solubility rules to determine if that's true or not. All right, so suppose you mix together nickel 2 chloride, NiCl2, and sodium phosphate. Will a precipitate occur? All right, so what's going to happen since nickel chloride and sodium phosphate are both soluble? We're going to have all of our different ions, the nickel ion, the chloride ion, the sodium ion, and the phosphate ion. So we already know the nickel and chloride do not stay stuck together. They stay dissolved. We know the sodium and the phosphate will stay dissolved. They don't form a solid. And so we're just going to look at what are my other two possibilities. Well, keep in mind that two positive ions, the nickel and the sodium, will not combine together because they're opposite charges. They're not going to go anywhere near each other. So we really only have two other possibilities. The positive ion from one going with the negative ion of the other compound, and then the positive ion from the second compound going with the negative ion of the first compound. Okay, so let's look at those again. So again, we're going to swap partners. The nickel is going to go with the phosphate and the sodium is going to go with the chloride. But now we have to be careful because just because nickel is a +2 and chloride is a -1, but when nickel joins up with phosphate, it's going to have a different ratio. Okay, so we call this an exchange reaction or a metathesis reaction. Again, the nickel and the phosphate go together, but notice that because they swap partners, they have to readjust their ratios or figure out, just either with a new partner, so they have to go by new rules or figure out how they're going to adjust to each other. Well, because nickel is a +2 ion and phosphate is a -3 ion, they have to form a compound in a 3:2 ratio that you see here. So three nickels in each +2 will give me a total +6 charge. Two phosphates, each with a -3, will give me a total -6 charge. And so these are balanced. Whereas nickel with the chloride on the left-hand side, you can see is nickel +2 and Cl-, and so that's why they're in a 1:2 ratio. So when they swap partners, they also have to reform compounds with the new ratios that will balance their charges. And then you can see over at the far right, NaCl, because Na is a +1 and Cl is a -1, just because they came in different ratios with their other partners, now that they're together, they only have to be a 1:1. So you might say, well, heck, this isn't balanced, and you would be right. So the next step would be to balance. So just a quick looking, we have two phosphates on the right, so we need to put a 2 in front of Na3PO4. We have three nickels on the right, so we need to put a 3 in front of nickel chloride. And now we have 6 chlorines and 6 sodiums, and so we have 6 NaCl on the right. Now we need to just kind of go through and see what's soluble and what's not soluble. So we kind of assumed that the first two were soluble, but let's double check it. Most chlorides are soluble, but and nickel is not an exception. Everything with sodium is soluble, so Na3PO4 is soluble. On the far right, anything with sodium is soluble, so NaCl is soluble. But now most phosphates are not soluble, and nickel is not one of the exceptions, and so nickel phosphate will be the one that is the precipitate. All right, so again, I just said this on the last slide, but the nickel and the chloride are both the chloride are aqueous, but the nickel phosphate and this is a solid. So it's the one that's not soluble. So you can put these symbols in. And then finally, we can do what we would And we can write the equation on an ionic level, and so we can rewrite it as an ionic. So first, everything that is a strong electrolyte will break apart. So we have 3 Ni2 plus and 2 times 3, which is 6 Cl minus. We have 2 times 3 again, sodium, and then 2 phosphates. And then on the right, the nickel phosphate has to stay as a solid, so we keep that together, and there were 6 sodiums and 6 chlorides. We can see that the chlorides and the sodiums are spectators, so we can cross them out. And then we have our essential net ionic equation. 3 nickel, 2 plus 2 PO4 negative 3 gives me Ni3 PO4 2, which is a precipitate. It takes a lot of practice, and so I would recommend going over some of these equations and practicing them. There's some on the study guide for the test. There may be some on the OWL. This is probably one of the hardest ones right here because you had to really think through, but all of them you have to remember that the new compound doesn't stay in the same ratios as the original, or at least not always. You have to readjust the ratios of the ions to suit their new partner. All right, and this is just a picture that at some point you may have already, or you may not yet. Would be a mixture of magnesium chloride, which is soluble, and silver nitrate, which is soluble. And then when you mix them together, you can see that a white solid is being formed, and that's a precipitate. So this is the end of the first section of chapter 4. You can continue on with the second one next.